wanted to give a few updates before we get going. First one, excitingly, I want to introduce our new Forever Green Initiative Executive Committee. So let's have a round of applause for George, Praveen, Josh, Jess, Jake, and Kevin. And they'll be serving on that committee along with the management team, Don, Nick, Colin, and myself. So this was the result of, for folks who haven't been as up on the process or involved, this was a result of faculty members having the opportunity to self-nominate and then to vote. So, and these are folks with active, ongoing Forever Green Initiative, research programs who are involved in those programs. So, yeah, really exciting. We got a new generation of leaders coming online to help stabilize Forever Green and move us into the future. And we have a wide range of backgrounds and expertise on the committee, which I think is a great thing for us moving forward. So yeah, many thanks to everybody who ran and to everybody who voted, and of course to the folks who are now going to be serving. I also wanted to give an update because last time I shared, I think, a date when our new RFP would go live. It's minor things, nothing controversial has come up, but we're just trying to nail down the final edits with the Office of the Associate Dean for Research, and we're not quite there yet. We're super close. So there's a chance that RFP will come out today. There's a chance that it will come out on Monday or maybe Tuesday next week. So very soon. And then just because that date moved, I moved the due date as well to the end of October. So everybody should have about 5 weeks. Again, we're hoping that or expecting that many of these proposals will be adapted from the last round, that folks who didn't receive the funding they need to keep going. So hopefully it's not too heavy of a lift for those groups. So we didn't leave a huge amount of time, but hopefully 5 weeks should be enough. And then again, they'll be announced around the end of the year, beginning of next year. And I just wanted to clarify one more thing. Last time we talked about 3 new funding pools. There was a little bit of, I got some feedback that some people weren't sure where they fit as far as which pools they should be applying to. So the first one is what I just talked about. It's basically equivalent to past Forever Green Initiative grant programs, funding the research activities of this group of people. Then the second one is a little different. This is going to be run by MDA. It's coming from the same source at LCCMR, but it's really aimed at for-profit companies primarily who are in the value chain, who are starting or growing businesses that are related to commercializing continuous living cover crops. So less relevant for folks like us at the university, although I imagine a lot of you have partners who are in this category and might, if you have names of companies or people that you'd like to see included in the stakeholder engagement that goes up to developing this program, you can email me or email Colin or both, and we'll make sure to get that person, those folks on the list. And finally, the third one is there's going to be base funding for Forever Green starting next July. We don't have a lot of answers on this one yet. The process is going to be worked out over the coming months. So stay tuned on that one. And I don't want to cut into our presenters' time anymore, so I'm going to leave it there, but I will pause for a second in case anyone has questions. So feel free to just pipe up because I can't really see hands too well. So if you have a question, go ahead and jump in. Okay, great. I'll stop the share and hand it back over to David.
Yeah, go ahead. All right, it's up to you. It's all yours.
All right, thanks a lot.
So I'm going to turn it over to David Mulla and his team to give us an update on the impact of Kernza intermediate wheatgrass systems on water quality and nitrogen mobility in the systems. As you guys, a lot of you know, there's been a lot of work done in this area, and David is pulling it together, and I hope will be giving us some modeling evidence and that can be used in policies and the placement of these types of systems on the landscape. So with that, it's all yours, David.
Thank you very much, Don, and welcome everybody, and thank you for attending. So let me share my screen. All right, the technical issues here are kind of confusing to me, so I'll just go with what I have now. The co-authors on this talk are Mohammed Tahir, who's a researcher working with me, Jess, and Jake Jungers. Obviously, myself and Mohammed, along with Jess, are in the Department of Soil, Water, and Climate, and Jake is in the Department of Agronomy and Plant Genetics. And I'm sure everybody on this seminar knows what we're talking about. We're talking about the deployment of perennial crops like intermediate wheatgrass or kernza, which is commercially viable and has some traits that can really help to prevent nitrate leaching to groundwater. We have a lot of issues in Minnesota with pollution of shallow groundwater and deeper groundwater, primarily in sandy areas of our agricultural regions. And so this was one of the driving forces behind funding research to identify the impact of kernza on the water balance and the nitrogen balance. And these are deep-rooted crops. Let's see, it's not advancing on this. So I'm gonna have to stop sharing for a minute.
I'd love to turn it into the PowerPoint presentation after I share
It's not showing the same thing that I'm seeing on my screen, so that's the problem. So I'll just close it and then come back. All right. So now I'll share this.
Yeah, try sharing that. Yeah.
All right, here we are. Anyway, as I was saying, the perennial crops like kernza have deep rooting systems, and this photograph from the Land Institute shows very clearly, you know, the deep rooted systems that we're talking about relative to the shallow rooted systems of wheat or corn or soybeans. And as a result, there's been the idea that these crops can remove water and nitrate from deep in the soil profile and prevent leaching of nitrates down to the groundwater. Also, they don't need to be fertilized as much as the row crops that they're replacing. And so if markets could really develop to commercialize the grain that's produced, it would be a win-win situation. So, you know, we started talking about doing research a number of years ago, Don and I and a number of other people. And we're making good progress on understanding how kernza takes up water, how the water dynamics affect percolation, how they affect evapotranspiration, and then how those two factors affect the nitrate leaching below the rooting zone. And water and nitrogen are really essential for the growth and production of kernza as well as any other crop. And so this is why we wanted to study these aspects of the water and nitrogen balances. We decided to establish some experimental plots in Lincoln and Pipestone counties where there is some serious concern over contamination of groundwater that's used for domestic drinking. There's about 146,000 hectares of cropland in these two counties. And this is divided mainly among continuous corn, soybeans, alfalfa corn, and then in alfalfa corn, soybeans, the dominant rotation is really corn, soybeans, 86% of the land. And that contributes a huge amount of the nitrate loading to groundwater. So the thought is if we can replace significant acreages of corn and soybean with Kernza, it could help to reduce the leaching of nitrate to the drinking water source management areas. So our objectives were to really evaluate, the production of Kernza, the effect of Kernza on the water cycle and the nitrogen cycle, and then to use the data from our experiments to get an idea of if we were to extrapolate over longer time periods and over larger areas, what could be the benefits of growing Kernza with regards to not only biomass production, grain yield, but also decreased percolation of water and nitrate.
Hey, David, I hate to interrupt you, but those of us on Zoom are only seeing the title slide.
They're still only seeing this title slide. I don't understand that. All right. This is a problem. All right, hold on. I'm gonna stop sharing. All right, can you tell me what you're seeing now?
I'm now seeing the study field location slide.
All right, that's the one we're on now. So
great.
Hopefully this will work better. We have two study field locations in southwest Minnesota. One is in Laverne, the other is in Edgerton. Both of them have a range of different rates of nitrogen applied to the plots from 0 to 60 kilograms of nitrogen. These are replicated and randomized. And can you see the next slide now?
Yep.
All right, good. We're taking measurements of leachate using suction cup lysimeters. And this is at 50 centimeters. We're measuring soil moisture content at 2 different depths. We're doing soil sampling to characterize the nitrogen and organic matter contents as well as other nutrients. We're measuring precipitation on site. And then we're taking the samples of soil and analyzing them for carbon and nitrogen. We measure biomass during the growing season and yield at the harvest. And then we're using satellite estimates of evapotranspiration to get estimates of biomass and evapotranspiration. This is a photograph taken at the Laverne site last year, showing the very healthy crop of Kernza that developed. And this was taken earlier this year at the Edgerton site, showing the boundary between the Kernza that received 60 kilograms of nitrogen on the left and 0 nitrogen on the right. And our goal is to use the data from the experiments to use the DSAT model to forecast yield, biomass, water balance, and nitrogen balance relative to row crops like corn, and then use the validated model on a wider scale and across longer time periods to evaluate the benefits from growing Kernza on large areas over drinking water source management areas and the impacts of doing that on the water and nitrogen balances. So at the present time, we've chosen to use the DSAT model because it has very sophisticated routines for weather management, soil and plant growth. There's a lot of detailed dynamics that are important to represent in the model. And we're basing the modeling of maize on the series maize submodel of DSAT, and we're basing Kernza on the perennial forage model of crop grow. Now, we only have a short time period for monitoring the Laverne and Edgerton sites. So while we've been collecting data, I'm not going to show you the results of modeling the data from those two sites. Instead, I'm going to show you data from a completed study that Don Wise, Jake Jungers, and myself conducted from 2013 to 2015 at Lamberton, Waseca, and Crookston. So these are completed experiments which have a lot of data of the type we're collecting at Laverne and Edgerton. And the idea is when we get enough data from those field sites in Laverne and Edgerton, we'll use those for the modeling. So the experimental design for the 3 other sites was pretty much similar to what we're doing at Laverne and Edgerton, except it'll be maybe a little bit more comprehensive. The cropping systems that were compared were corn and soybeans cropping systems with an intermediate wheatgrass cropping system. And we used 3 different rates of fertilizer, a control, a medium, and those 2 are similar to what we're using in Laverne and Edgerton. And then we had a high rate, which was needed for the corn. So here I'm showing you the results of our DSAT model simulations at the Crookston, Lamberton, and Waseca sites for the calibration and the validation periods. We're using the experimental data for grain yield, biomass, and soil moisture, along with soil nitrate leaching to calibrate our model. And then we're using measurements of those parameters in the last year of the experimental study for validation. And we're using a Nash-Sutcliffe equation, which is shown at the lower right, to evaluate the accuracy of the model. And it basically consists of comparing the observed and the simulated values. And the values range from -1, the theoretical values of this Nash-Sutcliffe equation range from -1, which is very bad, to +1, which is very good. And anything that's over 0.5 is excellent. So you keep that in mind when you're looking at the results in this table. What we found was that our ability to predict grain yield for both corn and intermediate wheatgrass during calibration was very good. And for biomass, it was also very good. We had excellent ability to predict soil moisture. And we did a little bit worse on nitrate, but it was still acceptable. And the poor performance on the nitrate is expected because this is a parameter that's difficult to measure. It varies a lot spatially and temporally. And in the intermediate wheatgrass experiments, the concentrations were really low. So almost like near, the detection limit for nitrogen. So this is part of the reason why the numbers are a little bit lower on nitrate. During validation, and this is typical, we always see the accuracy levels go down a bit, but they're certainly still very good, especially for the biomass and moisture, and less so for the nitrate. So this gives us confidence that the model can actually work very accurately at these 3 sites. So now I'm going to use the calibrated and validated model with a 10-year sequence of weather data. So well beyond the 3 years of weather data that were experienced during the experimental period. And what you see here is a summary of the grain yield and the biomass for the different rates of nitrogen fertilizer at the 3 sites. And so biomass and grain yield actually were highest for all three sites and on both crops at the highest rate, 160 kilograms per hectare of nitrogen. However, in the intermediate wheatgrass, the difference between the high rate and the medium rate, which was much lower, 60 kilograms per hectare, is not very large. It's actually very close. So from an environmental perspective, there's a lot of advantage, to just going with a 60 kilogram rate if you want to maximize grain yield and biomass for the intermediate wheatgrass. Obviously, with the corn, there is a significant advantage to the higher rates of nitrogen, and there's a significant drop in yield as you go, and biomass as you drop down to 60 kilograms per hectare of nitrogen. All right, so that's probably not unexpected. A lot of you already know that that's what we would expect. But one thing that has not been well studied with Kernza is, the rate of evapotranspiration, which is the dominant part of the water cycle in all agricultural crops. Evapotranspiration is always about 70% of the incoming precipitation. So if you're looking to understand the water balance, you have to start with evapotranspiration. And so this graph shows the annual ET of intermediate wheatgrass and corn for the three locations, along with the mean across all three locations. And it's separated out according to 0, 60, or 160 kilograms per hectare of nitrogen. And what you can see is that on average, the intermediate wheatgrass has higher annual evapotranspiration than corn for any corresponding rate of nitrogen. And even if you compare for the three sites, if you compare the evapotranspiration for intermediate wheatgrass at 60 kilograms of nitrogen, it's still higher than the evapotranspiration for corn at 160 kilograms. So there is a benefit in terms of Kernza extracting more water from the soil profile over the year than the corn crop. And this has important implications for other parts of the water cycle as well as the nitrogen cycle. All right, so I'll show you what I mean here on the next slide. The next slide shows deep percolation, which is a much smaller percentage of the water balance than evapotranspiration. So this is the amount of water that percolates below the rooting zone. And what you can see here is planting intermediate wheatgrass and application of the optimum nitrogen fertilizer markedly reduces the percolation of water. So for example, averaged over all three sites, intermediate wheatgrass has about 100 millimeters of water percolating below the rooting zone, whereas corn at 160 kilograms has about 130 or 135 millimeters. So it's about a 30% difference. 30% more water is percolating below the rooting zone with corn than with intermediate wheatgrass. And what is that water carrying? Obviously, it's carrying nitrates. So the two components that affect nitrate leaching are, what's the volume of water that's being transported below the rooting zone? And what's the concentration of the nitrates in that water? So these are the two parameters that are important. So next we get to the nitrate leaching losses. And these are in kilograms per hectare. So it's really the product of the nitrogen concentration in the water percolating below the rooting zone multiplied by the amount of water percolating below the rooting zone. And the model is calculating the nitrate leaching losses on a daily time step over this 10-year period which has a large range in weather conditions. And what we see here is a tremendous difference, tremendous reduction in nitrate leaching for the intermediate wheatgrass relative to corn. It's about a 10 times lower mass per unit area than we see leaching with the corn. And obviously this also is a function of the rate of fertilizer. So when you're applying 160 kilograms of nitrogen to corn, that is resulting in about 25 kilograms per hectare of nitrate leaching below the rooting zone. When you're applying 60 kilograms per hectare of nitrogen to intermediate wheatgrass, the nitrate loss is about 2 kilograms. It's about 10 times lower. So again, this offers the possibility of protecting groundwater at a very, very efficient level. And that's why there's a lot of interest in exploring the planting of intermediate wheatgrass in drinking water source management areas. All right, the last experimental result I'll show is field observations versus modeling of the soil moisture profile. So we've taken the data for all 10 of these years and just plotted the data on, oh, I'm sorry, I think this is just 3 years of data, just the experimental years for simplicity. And the blue and purple colors indicate moisture contents for intermediate wheatgrass, whereas the red and gray indicate the moisture content for the corn. And the first column is for Lamberton in 3 different years. The middle column is Waseca, and the last column is for Crookston. So what you can see here is the dots, which are the measured values, and the lines, which are the model values. They compare very closely. So the model is doing a good job at predicting moisture content. And secondly, you see that the moisture contents for intermediate wheatgrass are always lower than for corn, meaning the intermediate wheatgrass is extracting more water from the soil. That's why we have higher evapotranspiration and lower percolation. And the corn is not extracting as much water. That's why it has lower evapotranspiration and higher percolation. So this graph is really instrumental in helping us understand the water balance and how it differs for corn and intermediate wheatgrass. So I didn't want to draw this out too much because I know there's probably a lot of questions. So I want to conclude here. I want to say that IWG produced higher biomass than, well, it produced high biomass under rain-fed conditions, and so it's very commercially viable. It reduced deep percolation by about 30% compared to corn by using soil profile moisture efficiently. It reduced soil nitrate concentration as well as loadings by about 10 times relative to the maize crop. And so environmentally, this has a lot of advantages when you grow intermediate wheatgrass at 60 kilograms of nitrogen. So when we get done with collecting our data at Edgerton and Laverne, and we'll have results from 2 years very shortly, probably by the end of this year. And that will be enough data for us to actually begin doing some of this model evaluation. We have a calibrated model that works at Lamberton, which is very close to Edgerton and Laverne. So our thought is just to take the calibrated and validated model from Laverne and apply it without any more adjustments and see if we can use it to predict the water and nitrogen balances at Edgerton and Laverne. If some additional calibration is needed, I mean, the results will show us whether there's a significant difference due to spatial variability between Edgerton, Laverne, and Lamberton, we'll be able to identify whether or not additional calibration is needed to address that spatial variability. I want to thank the Clean Water Land and Legacy Amendment for providing funding. This money was passed through the Minnesota Department of Agriculture to the Forever Green Initiative. And so I want to thank those two entities as well. And I want to thank all of the members of, my team, Jake Jungers, Jess Gutknecht, Mohammed Taher, Don Wise. All of this collaboration has really been very productive and fruitful. And I would like to thank the audience for attending, and I open it up now for questions. Thank you very much. All right, Jake has a question.
Based on the calibration data set that you use, the diversity of soil types and the range, the geographic range data for that calibration data set, at what scale could we start to use the DSAT beyond those sites in Minnesota? How far outside of Minnesota could we go to start to predict water quality impacts of current plantings in the upper Midwest?
All right, great question. Yeah, I will repeat the question. Jake Jungers asked, given that we've calibrated and validated the DSAT model at 3 diverse sites in Minnesota across a long climatic record, is it possible for us to extrapolate the model to other sites in the Midwest and estimate the environmental and productivity benefits of growing Kernza at other sites, maybe in Iowa or Illinois or Indiana or who knows where? And I mean, I would say, with what we have now, we certainly can go ahead and try doing some of those kinds of simulations. We probably would want to know which soil types are most like the soil types that we did the calibration and validation in Minnesota. So for example, the Crookston site would be a heavy clay probably. And I have those soil types listed earlier in the presentation. Lamberton would be, a bit coarser textured. Waseca would be a bit coarser textured than Crookston as well. And obviously there's differences in precipitation. So I think we could look for soil types in other states that are somewhat similar to the ones where we already have calibrated the model, and first start to do some exploration on those kinds of soils. Obviously, the model should be transferable to other weather regimes. I'm not as concerned about that. If you change the weather regime, the model doesn't really have to be recalibrated for any reason whatsoever. But when it comes to, running the model on different soils, that's a bigger concern. So I hope I answered your question a little bit there. All right, Jess, you had a question as well.
Yeah, and it was a little bit related to that and the applicability of the model. And so another thought I have on that question is that, I wonder if you could start with like soil families almost and start there and see how applicable the model is with different soil families in different places. Because it seems like you have the environmental data, like the climatic data, more dialed in.
Yes.
Yeah.
Yeah, so Jess is asking if we can start with different soil associations or soil groups and base the extrapolation on those. And certainly, there's a coarse scale of soil mapping called StatSco, which would be something that we could take a look at, and we could use that as a basis for trying to do the extrapolation. The finer scale soils data in Surgo would be a lot more tedious to go through, but we could do an initial screening at the StatSco scale and then maybe narrow it down to specific soils within StatScope.
My real question.
All right, now Jess has
Sorry.
another question.
I was wondering, that was like the play after that first question. Yeah, I was wondering, like, in this, if you thought, or how you're thinking with this new study at Edgerton and Laverne of how to like keep validating the model for nitrate. So when you showed the model doesn't perform as well with just base nitrate levels because it's such a complicated cycle. Like, is that just in DSAT, like, is that just is what it is and it's always going to perform that way? Or do you have ideas about how to improve our ability to like actually predict the nitrate underneath this crop?
All right, so Jess's question is about how we could go about addressing the issue of low model accuracy when we're trying to predict nitrate by maybe collecting other measurements at Laverne and Edgerton. And yes, I think there are ways of addressing that. One way would be to collect more samples. Another way would be to focus maybe more on trying to predict the model's ability to estimate residual nitrogen at the end of the season, which would be a kind of measure of the cumulative impacts of the nitrate leaching. So if you have a lot of nitrate leaching, then you would see lower residual nitrogen values in the soil profile after harvest. And so that's something that's much easier to measure and more accurate to measure than the individual concentrations at a small, location and on individual days. The other opportunity would be to just install more lysimeters and have a more dense network, which is a lot of work.
Yeah.
So if someone wants to volunteer, maybe that's what we need.
We should let volunteers know that it's also an 8-hour drive.
Yeah.
Good for people who like podcasts.
Right.
How far are these?
How far are these sites? They're spaced probably about 100 meters or so from each other.
Yeah, you have your picture in the beginning.
Yeah, I'll go back up to that.
Plots are 2 hectares. So when you go back to that.
All right, I'm trying to get up there.
Very large.
Right.
Yeah.
So Jake, you want to describe the dimensions here?
Well, they're about 2 hectares in size. I don't remember.
All right, they're 2 hectares in size. I think they're 50 meters wide or something like that. So it's not a huge area, but we are only taking measurements at about 8 locations. So it's a pretty small sample number.
Yeah. But one thing that I think is interesting about the design that I wonder if could be leveraged is if you click on the next slide, the fact that we have this really close spatial proximity of the fertilized, unfertilized.
Right.
So that almost, the soil type and all of those other variables are very close, are very similar when we're comparing fertilization, at least.
Right. So Jess is making the point now that we're already leveraging the fact that, our sampling is right along the boundary between adjacent treatments for fertilizer rate. So on the left side would be an unfertilized plot, and on the right side would be a fertilized plot. And we're taking measurements on 3 meters, 3 meters away from the boundary on either side. So, we have a good paired comparison. And we're not inducing a lot of spatial variability by sampling at really widely spaced intervals. So that's the reason why we chose this design. Are there any questions online? I know we have quite a few people online. 21 people.
Dave, Nick Jordan here.
Oh, hi, Nick.
Hey, thank you for this wonderful work. My question to you guys is, if we step back and think about where we want to get to in 5 years, from a science point of view, from a policy relevance point of view, what are your thoughts on that? What are the team's thoughts on that? And here we have a plant that we would expect to behave as it's expecting. It seems to me, naively. And I'm wondering if there are new leverage points yet to be discovered, meaning that my naive perspective is probably wrong. Or, what are your thoughts about where we want to be in this whole work of evaluating the hydrological and nutrient cycling effects mediated through water of Kernza? What do you guys think about that?
Well, I think the idea is to, with this model at least, we can explore some different scenarios for rolling out or accelerating the planting of Kernza in areas that have vulnerable groundwater. And so we can answer questions like, how many acres does it take of Kernza planting to reduce groundwater nitrate leaching in the drinking water source management area by 30%, for example? We could choose a goal, a 10%, a 30%, a 50% goal, and just see how many acres it might take of Kernza plantings to do that. Now, Nick knows that we've already done some modeling of this type in the Rogers Creek watershed. And we've run through some scenarios where, we kind of estimate how many acres of Kernza it might take to reduce nitrate leaching by 50%. And it turns out, that we have some estimates on that. So I think the plan here would be to run these models for different locations with different goals in mind, keeping in mind that there's economic trade-offs for replacing corn and soybeans, and that there's environmental trade-offs of those land transitions as well. And I think the other thing that with this model we can do is we can investigate climate resiliency. We can look at running future climates with Kernza and without Kernza to see how much benefit there might be in the future years as our precipitation patterns change. So those are a few maybe thoughts about how we might proceed, but my overall assessment is there's a lot of potential for accelerating the adoption of Kernza in drinking water source management areas. And it isn't going to take, huge acreages. I mean, we're not talking about replacing all corn and soybeans in the drinking water source management areas. We can achieve, because the leaching losses are so much lower with Kernza, that strategic plantings on 25% of the land or 30% of the land could achieve significant environmental benefits. And that could grow over time as the markets for Kernza grow. So there's an opportunity for not only achieving environmental goals, but also maybe a potential for labeling Kernza with some, environmentally or green labels that would indicate to people that when they purchase these crops, they're helping to protect groundwater in Minnesota, and that this is a very sustainable practice. So I think that these are some of the ideas that I just wanted to propose, and I'm sure other people have a lot of ideas as well, but it'd be really wonderful to have more dialogue on some of these ideas for future planning.
Well, Dave, if I can follow up briefly, every bit of that makes a ton of sense to me. So, particularly as we think about something like a label, how close are we in terms of model performance, especially in terms of making broader inferences, as you were describing? How close are we, to having models that you think would, decently substantiate, say, label claims, like whatever that means, right?
Yeah. Well, I mean, I think we're pretty close on, some of the critical soils in Minnesota. And, it might be another thing we should try perhaps is taking data from other sites where you have different kinds of soils. Now we have quite a bit of rollout of Kernza all across the state on different soil types. So as the data comes in, these models can be used to basically assess the performance on a wider range of soils. And then we get that much closer to being able to substantiate our claims for how these perennial crops perform on a wide range of soils across a wide range of climates.
Mm-hmm. Thanks.
Nick, I think it's also worth noting though that from the brain on the parade, that there's still assessing like the fertility needs of Kernza and a lot of other things. I mean, all of your data, David, on the water use are really exciting because that implies that as we learn more about the proper fertility, we will still see really promising reduction in soil nitrate. But there's still a lot of things in this crop that I think are gonna still keep going hand in hand also.
Right. Okay. So Jess just mentioned, Nick, if you didn't hear her,
wants to disagree with me, do it. But
that although we're very close perhaps on the water balance and the nitrogen cycling, it might be worthwhile to pay a little bit more attention to the soil fertility and how that varies across different soils.
Well, there's always a malcontent in the mix.
sorry.
So the question I have.
Okay, Don has a question.
We have a group of breeders across the country, Canadians, Utahns, folks from Kansas and here that are thinking that, reminding everyone, this is Kernza 1.0, right? You show that there was, extensive biomass being produced below ground and above ground, but only a small portion of that is grain, right?
Right.
So the breeders have made the decision that they want to market the grain into the grain market rather than into the forage market to some degree, right? There's always going to be a market for both. So what is your advice to these breeders? In terms of ET and the reduction of water moving through the system, but there's this other piece. What is the efficiency of uptake of nitrogen because of that dense root? What is there an efficiency of nitrogen uptake? There's a high level of water uptake. What's the advice that you're going to give the breeders about how they should, as they move towards producing more and more grain, maybe maintaining the same level of biomass with the grain, but changing the architecture of that plant? What advice do you have for them?
All right. Did everybody hear the question online? All right. I won't repeat it. Okay.
Yes.
Good. So one of the things that we can do as modelers is we can, the model has parameters in it. And so here's an example of some of the parameters that we're using in the model. Let me see if I can increase the size of this a bit. It's kind of hard. Okay. Anyway, the point is that we can work with breeders to look at certain traits that they might be interested in changing to get higher grain yield. And we can examine how changing those traits might affect some of the parameters in the model. And then in real time, we could run the model to see what impacts those changes would have on nitrate leaching and evapotranspiration. And I think that might be a lucrative way of proceeding. We can also sit down with breeders and just talk about what traits are in the model. And they can perhaps give us ideas about how to go about looking at changing those parameters to give them ideas on the sensitivity of the outputs to the parameters that they're interested in breeding for. Yes.
This is a follow-up to that. I just want to make, maybe you were already aware of this, but the Kernza breeding program, I think, is working with Jake, looking with cameras, looking at the full array of germplasm to look at differential root development, right? So I think it would be great to make sure you get linked into that right now as that data is being generated to make sure.
They're just starting that this fall, and I think Ravine's on. Ravine's online and to talk about that, but I think they've selected. Yeah, you say it, Ravine.
Yeah, I was going to ask. Can you hear me?
Yes.
Yeah.
Okay, perfect. I was going to ask David. Great presentation. Is it possible to measure some of the traits in our spaced plant nursery, or is it mostly on bigger plots that you're operating?
I think you could probably get it. You could get started by measuring them in the greenhouse if it's quicker, and then there's a phase where you want to scale that up to the plots, and then obviously to a commercial level.
So the population that Don mentioned, Jake and I are collaborating on this project where we are going to look at 150 diverse space plants that are genetically tracked, so we know their genetic composition. And I can see the value of your models in maybe trying to look at, I'm not sure how many we can measure, but all 150 or maybe a subset of that, and combine that data with the root architecture data that we're going to collect starting early next spring. So maybe I'll send you an email with Jake included, and we can discuss.
All right.
Yeah, I just want to make sure you guys were connected to make sure that if you have information that they should collect to match the model, I want to make sure that
right.
is on the table.
And we certainly have some good suggestions that we can make with regards to parameters that are related to nitrogen uptake and parameters that are related to, leaf area index and how that develops over time, parameters related to rooting growth, because those will affect the nitrogen and the water cycles.
Yeah.
Right.
What's the relative importance of the evapotranspiration rate itself versus the water use efficiency? Because you made a note about efficiency on your very last slide, and I was wondering, because it seems like if you have a lot of evapotranspiration, that's actually a low water use efficiency. Like it seems like, unless I'm not understanding it right, because if you're sucking up a bunch of water and blowing it all out, you're not using water very efficiently. So I'm wondering, like, how you in the modeling world think about the importance of those different things.
Okay. Yeah, I think water use efficiency is a little different than evapotranspiration. Normally, when you talk about water use efficiency, it's how much yield or biomass you can create with a unit of water.
Right. Right.
And so that would really require taking the biomass and dividing it by the evapotranspiration.
And so in your last slide, when you talked about efficiency, what did you mean in that?
In the last slide, I just meant that, you know, the kernza is able to take up more water than the corn. And I probably shouldn't have used the word efficiency there. It probably was misleading.
Well, thanks for clarifying those concepts. Yeah.
Another question.
Well, it was a short,
Speak up loud.
it was just a short response to Nick's question and some feedback to the team doing this modeling. We implement a pilot project for the state of Minnesota that ostensibly is modeling, you know, groundwater, nitrogen leaching, nitrate leaching improvements based on kernza. But as far as I'm aware, there's no publicly available tool that you can model for a specific field or intermediate wheatgrass. So just incorporation of these results or the ability to model this exercise for a farmer's field anywhere in the state or beyond would be exceptionally helpful. Right now we use the nutrient tracking tool. And we basically do a corn soy standard scenario and then use the counterfactual assumption based on your great research that this is going to eliminate most nitrate leaching. But it's essentially many of those models are used as a baseline, you know, understanding of policymakers at state, federal levels. It's the ability, kind of the way that intermediate wheatgrass is being incorporated into common farm, that kind of thing. But water quality models that are out there, that would be very helpful. So that's kind of a response to Nick's question. And the other is that, you know, further leveraging this research to boost awareness at the federal level benefits. You know, we have a lot of support from state government so far, but kernza was not selected as a climate smart commodity, right? And I think it's because partially because it's such a new commodity, but the benefits are not yet widely understood, especially in other states. So I'm just kind of trying to give some feedback to Nick's question about some 5-year targets.
All right, thanks. Nick, did you hear that? I'm not sure he's online.
Jeff, do you have a question?
I do actually comment and question. So I think that was Colin's voice I heard there. So, and I think Isam Lakori, Pat Nash maybe joined this call earlier, but they are actually doing modeling on a DWISMA basis, as David knows, to address, you know, nitrate and groundwater, you know, before and after conditions using different cropping systems. So just a comment. So it's kind of interesting, you know, the things you guys are talking about here, you know, we're kind of, you know, debates, you know, we, you know, had earlier this week in forums. So there was a environmental quality board meeting on Wednesday where one of the board members asked, and this was more broadly continuous living cover, not specifically kernza or forever green crops, but she was asking, well, okay, so what? You have a state water plan, you know, you have a nutrient reduction strategy. You know, what's the number? How many acres of continuous living cover do we need in Minnesota, you know, to reduce nitrate and groundwater in this case, and surface water, to have, you know, impact on climate change? So I'm a policy guy, so I'd like to think, yeah, we have a number and we can assign some water quality benefit to that. So from a modeling point of view, David or others, what cautions do you give in kind of jumping to, you know, getting a number based on acres?
Yeah, I think, you know, that modeling has a role to play in helping to develop those policy goals. I have a lot of experience doing that. I know it was really the work that I did with Bill Lazarus a number of years ago that led to a recognition for the value of perennial crops in meeting water quality goals. And we were able to put actual numbers on how many acres needed to be planted to perennial crops to protect surface water, what it might cost. Now we're in the process of doing the same kind of exercise with regards to groundwater. We're working, as you know, very closely with the Minnesota Department of Agriculture to provide them with modeling tools to answer those questions. And we're actually supplying them with, you know, the modeling approaches that they're using on a duisma by duisma basis to make exactly those kinds of assessments. So that's all in progress right now, and this work is certainly going to contribute to that.
How about the climate change part of that? So continuous cover for, you know,
Right.
carbon sequestration, and then actually what I'm more interested in that I don't hear a lot of talk about is, you know, continuous living cover, whether it's current or otherwise, for nitrous oxide reduction because of less nitrogen used and because it's better utilized by the plants. So any thoughts on that?
Yeah, that's a good idea. I think, you know, those are both avenues that need to be pursued, and thank you for bringing them up. There are efforts underway to sort of address those, but they're not as far along as the material that I've been talking about today.
Yeah.
Jess has something she'd like to say.
Yeah, we do have those efforts underway. So one of the newer Forever Green funded grants, we were really fortunate to get a Forever Green funded grant that leverages this a very large fertility experiment. And it's only here at the Minnesota site, but the Kernza Cat project that maybe people are familiar with has a large fertility experiment with many, many different levels and ways of fertilizing Kernza. And this new grant then layers on the greenhouse gas emissions work and the full like nitrogen balance and nitrogen use efficiency, including in the different yield components, and kind of a deep dive into how is Kernza using nitrogen, how is it flowing into the groundwater, because we already have like scimitars in this other experiment, and then how's it being blown out into the atmosphere. So we're just finishing up the first year of data, which isn't a great year to report on either, because it's when Kernza is at its leakiest, because it's still getting established. But yeah, so in the next couple of years, you know, we'll start having data on that experiment. So
Okay, thanks. Yeah. We look forward to seeing those.
Yeah, and you're right, Jeff, that like this is a really promising thought process, but almost no one in any crop has connected those pieces. So there's starting to be this evidence that if you use nitrogen well, you're cleaning the water in the air at the same time. But I think that's a really new line of thinking that people haven't explored as much yet. Unless, do you know of much research in that area, David, either? Or
certainly not with Kernza. There's a little bit on camelina. That Jason has just completed, Jason Hill and his postdoc. And I'm involved in a USDA Sustainable Ag Systems project that's actually working with Jason, and we're modeling the greenhouse gas emission fluxes from camelina.
Yeah, and I know Russ, who's on the line, is starting to do some of that work as well. I believe they were starting to look at greenhouse gases this year.
All right.
Well, Josh Gamble has, you know, a major project out of Rosemont on camelina. And that's a big project. I don't think he's online, but there's another whole group that is looking at camelina and pennycress as part of the USDA program here in the state. So
yeah, do they have, and I know in our project with Josh, with his Ediflux towers, he was thinking about getting a nitrous oxide sensor. I think so far that's the carbon side of things. So I don't, yeah, and his other work with the USDA, I'm not sure.
But all I'm saying is there's another group
balance
that is funded through
right.
Forever Green that is trying to take on that challenge in terms of looking at not just Kernza, but the continuous living cover framework. And I would argue it is probably the most underfunded part of continuous living cover efforts. A lot of folks are pretty comfortable with the water part and nutrient management to some degree, but the whole greenhouse gas part is, in my opinion, needs a lot of additional effort.
Carbon's complicated.
Yes.
Yep. Yeah, so in that, and actually that's a great advertisement, Don, because Josh and our team for the Forever Green Funded Project are giving this presentation next week.
Okay,
So
stay tuned next week.
yeah,
There'll be a lot of answers to these questions.
well, yes or no, but yeah. Either answer.
All right.
Well, thanks everybody, and thanks to you, Dr. Mulla, and the team for your presentation today, and a great update on the activities of the past and things that are coming up in the future. And again, I would invite all of you to come back for more of this type of information discussion next week, Friday at noon. Thank you.
Bye-bye. Thank you, everybody.
Bye.